let's take a look at some interesting limit examples that hopefully will ring a bell. What we're going to do is start with the function. Let's start with, say, f of x equals 2x. And now we're going to consider the limit as h approaches 0 of f of x plus h minus f of x all over h. Okay, what's going on here? Hopefully you recognize this as the definition of the derivative. It's actually a limit problem. And so what you'll actually be more inclined to see is something like the following. Just the limit as h approaches 0 of, and then what we're going to do now is use 2x. So what do? Well, it's 2 of x plus h, and then we get minus 2 of x all over h. Okay, so we've got sort of a 0 over 0 thing here, right? We need to go further. 0 over 0 is undefined. So we continue, we take the limit as h approaches 0 of, we get 2x plus 2h minus 2x all over h. And then fortunately, the 2x's cancel. And so we get the limit as h approaches 0 of what? Well, the 2x's cancel, we just have 2h over h. Well, that's just 2. Now this is interesting because there's no h in the expression, right? Limit of as h approaches 0 of 2. You can think of this in two different ways. One, if there's no variable there, it's just, you just ignore it. Or you could look at, okay, if you have the graph y equals 2, it's always just 2. So however you want to look at it, the answer here is in fact 2. Okay? So this is our first example. The marker flowing a little bit. Okay, so second example, let's consider the following. I want to consider f of x equals x cubed. Okay, and we're going to try the same thing. So by trying the same thing, what I mean is we're going to look at the limit as h approaches 0 of f of x plus h minus f of x all over h, definition of the derivative, which again is a limit problem. So what do we do here? Well, we just use our new function. So we've got the limit as h approaches 0 of x plus h cubed minus x cubed all over h. Now, this is a little bit, it's not that it's tricky, it's sort of like a pain perhaps because you've got to figure out x plus h cubed. Now, there's some different ways to do this. You could do it by brute force. I actually want to do it using Pascal's triangle. So let's take a look at Pascal's triangle. What is Pascal's triangle? Okay, so you've probably seen this before. You've got a 1 at the top, then you've got 1's underneath, and now you add in the middle. So 1 plus 1 is 2, and then 1. You get 1, 3, 3, 1. There's the beginnings of Pascal's triangle. Now, what does it mean? Okay, when you get to this point here, what it means is the following. It's good if you have some type of, I don't know, some type of function. In fact, we have one here, we have x plus h. So what it actually tells you is it tells you the coefficients. Okay, it tells you the so this gives us the coefficients of a cubic polynomial, of an x plus h cubed. Okay, and so when we multiply it out, the coefficients are going to be the following. Limit as h approaches 0 of what? It's going to be 1. Okay, 1 what? It's your first term to the highest power, so it's 1x cubed. And then plus, get a coefficient of 3. 3 what? What happens with Pascal's triangle is that x's go down in power as your other variable. It could be a number. Okay, it could be y, it could be h, go up in power. So the first one is really h to the 0, which is 1. And for h to go up in power, we need an h. but then we've also got x squared. Okay? And then we keep going. I wanted to write that as x squared h, but same thing. X continues to go down in power, we get an x. I'm using the second 3 coefficient here. And h goes up in power, we get an h squared. And then finally, we get simply an h cubed. Okay? So that is Pascal's triangle. And this is all going to be over h. And then we also need this minus x cubed. Okay. So, what next? Do the algebra. The x cubes cancel. Okay? And we can factor out an h. So, if we try those together, we get the limit as h approaches 0 of what? Well, that h is going to cancel out. So we get 3x squared. One of those h's will cancel out. Plus 3xh plus h squared. Okay, much more manageable now. And if we look at this, you can plug in 0 because you have a continuous function. And in effect, you are left with 3x squared. Okay? So, what does this equal? It equals 3x squared. Now, what did we do in these two examples? We figured out the derivatives, okay, because the derivative is a special type of limit problem. So the derivative of 2x is 2. Let's analyze a little bit what that means. So if you look at a graph of this, different color here. So the graph of 2x goes something like this. And the question, recall that the derivative answers is what is the slope of the curve at every given point? Well, y equals 2x, okay? This is y equals 2x. So the slope at every given point here is 2, right? It doesn't change, it's a straight line, okay? Now, if we look at the x cubed example, what does that look like in terms of a graph? Okay, well, x cubed, you should know, goes something like this. And the 3x squared is in effect giving us the slope at any given point on the curve, okay? And so, if you want to pick a point like this one, right? Not clear what that is, the tangent line goes something like this, and the 3x squared, you plug in the value, it gives you the slope, it gives it to you for every point on the curve. Now, I want to kind of take this one step further. This is going to be interesting. What if we continue with Pascal's triangle? Okay, let's try that. So we're going to continue with Pascal's triangle, and we will get 1, you just add up, right? It's 4, 6, 4, 1. Okay? So, imagine you have f of x equals x to the 4th. Okay? So, what might that look like? Well, in terms of limits, right? I'm not going to write out the limit, I'm just going to write out the function. But we're going to imagine it. What would happen when you take the limit of this function? Okay, what's going to happen is the following. You're going to have the limit, we'll look at part of it as h approaches 0, and you're going to have an x to the 4th plus 4x cubed h plus, and then we're just going to say dot, 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 and at the very end, what's going to happen, you're going to get a minus f of x, so a minus x to the 4th. Okay? And so this is all in the numerator, and this would all be over h. Now, the point here is the following. The x to the 4ths are going to cancel. All the other terms are going to go to 0. And you're going to be left with something like this. The limit as h approaches 0 of 4x cubed plus, and these are just going to be a bunch of h terms. And so the answer is going to be 4x cubed. Okay? If you can sort of get this pattern that happened with the x cubed, you can really extend it to x to the 4th. Okay? And what this shows us is it shows us really the derivatives from Pascal's triangle. okay? So we did already x squared, and then, you know, what do we get when we took the derivative of x squared? We got 2x, okay? This is like the x squared term, okay? And then the row, I should say. And then this row is kind of like x cubed, and we just solved, we got 3x squared. And then this row, which I'm trying to suggest to you, when you, if you did all the algebra, I was just looking at the key parts of it, the only thing that would survive would be the 4x cubed. And so the derivative of x to the fourth is 4x cubed. And hopefully you can see a pattern. You could continue Pascal's triangle, and what would you get? Well, let's consider. What would we get? If we continued it, we would have a 5x to the fourth. And the idea is we're considering that that's the derivative of x to the fifth. Okay? So there is definitely a pattern here. Okay? And we will formalize it later. But I just want to show you how sort of, you know, you can use Pascal's triangle to kind of get an idea of what the derivative of really any x to some power should be.